Welcome to the 5th tutorial about the function blocks within the MOC logic. In the last tutorial we have looked at the function block Boolean to UI8 converter, which translates Boolean values into integer values. This tutorial is about the motion function block saveStop, which is used to trigger and monitor the saveStop of a drive system. During this process, the drive must be shut down in a controlled manner. In this way, the brake torque of the drive can be used to bring the drive to a standstill in a shorter time that would be possible with an uncontrolled stop. As a stop ramp for the drive system is normally non-safe, the function block saveStop monitors the actual reduction in the speed down to standstill. First of all, we take a look at the in and outputs. Let's start with the inputs. Like at the other motion function blocks, there's also the input motion, where the function block receives all the information provided by the encoders. Through the input standstill, the function block saveStop gets the information if the standstill conditions are met or not. The input saveStop 1A as well as the optional input saveStop 1B are normally high. If one of them goes low, then they trigger the function saveStop1, which induces the brake operation of the drive via an emergency stop ramp. This brake operation is monitored from the drive monitoring device. When the current speed is below the standstill speed, then the energy supply of the drive will be disconnected. For triggering the function saveStop2, there are the input saveStop2A as well as the optional input saveStop2B. These inputs are also normally high and trigger the saveStop2 if one of them goes low. At a saveStop2, the brake operation starts via an emergency stop declaration. This brake operation will be monitored by the drive monitoring device. When the speed is below the configured standstill limit, then the function saveOperatingStop will be used to remain the drive in the position where the function was activated. The inputs RampSelection0 and RampSelection1 are used to select between up to 4 configurable stop ramps. Last but not least, there's the input Stop2Reset, with which a saveStop2 can be reset by a rising edge after a standstill has been detected. Now we go over to the outputs. With the add of the outputs Enable Torque, Enable Brake, Amplifier Off and Stop Request, the drive system can be controlled. Enable Torque switches off the torque of the drive system. Enable Brake switches off the power supply to the mechanical brake. Amplifier Off triggers the shutdown of the amplifier, the drive's torque, and also engages the brake. And Stop Request triggers the stop ramp of the drive. In addition, there's the output Slope Active, which shows if a stop ramp is activated. With the add of these in and outputs, plus the appropriate configuration, this block can perform the functions saveStop1, saveStop2 and Save Brake Control. To have a closer look at the function block, we start in the hardware configuration of the FSD. This time I've extended the FlexiSoft station from the last tutorials with an XTIO module. Here I have connected an eStop as well as a reset on the inputs and a drive save torque off on the output. Now I switch to the MOC logic. Here the 4 function blocks which I explained in the last 4 tutorials are still located in the logic editor, because we need them in this example to integrate the function block saveStop into our MOC logic. At first I'm going to place the block saveStop in the configuration area. In the register function block, we select saveStop and place it via drag and drop below the other function blocks. At first, we take a look at the input motion. This input must be connected to the output motion of the function block speed crosscheck, so the save stop gets all the information provided by the encoders. Therefore, I create a source jump address, which I call motion, and connect it to the output motion of the speed crosscheck. After that, I add the corresponding destination jump address and connect it to the input motion of the save stop. Next, we consider the input standstill. Here we have to create a source jump address again, which we connect to the output standstill of the function block speed monitor. The output standstill goes high if the standstill condition is met, which means the motion speed is lower than the configured limit standstill for at least the duration of the standstill acceptance time, or the standstill position window is not exceeded. Now we also add the corresponding destination jump address, which we connect to the input standstill. The next input, called SaveStop1a, triggers the function SaveStop1. Because the function SaveStop1 is executed normally after an eStop was pressed, we have to route the signal of an eStop from the CPU to the MOC. Therefore, we switch straight to the CPU logic. Here I have already connected the eStop as well as the reset to a routing end-to-end function block. Because we need a reset button later on in the course of this tutorial to reset a SaveStop2, we are going to route the signal of the eStop as well as the signal of the reset from the CPU to the MOC logic. Therefore, we switch in the left sidebar to outputs, where we take bits 3 and 4 from the register MOC0 and connect it via the block routing end-to-end to the eStop and to the reset. After that, we switch back to the MOC logic. The output bits from the CPU, which are connected to the eStop and to the reset, are now available here as input bits in the register CPU0 of the tab Inputs. Because we don't need the signal of the reset till we have enabled the optional input Stop2 reset, we just take the signal of the eStop and connect it to the input SaveStop1a. Last but not least, there's the input SaveStop2a. With this input, the function SaveStop2 is triggered. The input SaveStop2a is typically connected via a jump address to the output monitor status of the function block speed monitor. After connecting, the function SaveStop2 is activated if the output monitor status of the block speed monitor goes low. This happens if the current speed at the input motion is higher than the configured max speed, or if the current direction of travel isn't enabled, or if the current speed is higher than the by the optional input speed enable ID selected speed limit. After the inputs are explained, we take a look at the configuration of the save stop. By double-clicking on the function block, the configuration menu opens. The first tab which appears shows an overview of the current configuration. In the tab Units, you can set the unit for the speed and the position values. Here the unit must match with the motion type of the encoders, as well as with the configured unit in the function block speed crosscheck and speed monitor. Otherwise, the block save stop turns orange and the configuration becomes invalid. Let's go further to the tab Stop Ramps. At first, we have the possibility to extend the inputs SaveStop1a and SaveStop2a with the optional inputs SaveStop1b and SaveStop2b. These inputs can be used, for example, if you want to trigger the functions SafeStop1 or SafeStop2 by a further safety switch. Next, we enable the optional input Stop2Reset, with which a SafeStop2 can be reset. Down here, we can select up to 4 stop ramps. With these we can define, on the one hand, a delay time until the start of the stop ramps, as well as a speed offset, and on the other hand we can determine the slope of the stop ramps by the parameters speed reduction and duration of speed reduction. Depending on the number of the ramps, up to 2 additional inputs can be enabled, which are called ramp selection 0 and ramp selection 1. If only one ramp is set, no additional input is required, what simultaneously means that only this ramp can be used to stop the drive. When 2 ramps are used, then the additional input ramp selection 0 is enabled. And if 3 or 4 ramps are set, the input ramp selection 1 is enabled in addition to the input ramp selection 0. These 4 ramps can be selected by this signal combination of the inputs ramp selection 0 and ramp selection 1. Let's pass over to the next step of delay timer. Here we can set the off delay for the outputs enable brake and enable torque based on the switching off of the output amplifier off. When the drive system is equipped with a brake, then the parameter off delay for enable torque is typically set greater than the off delay for enable brake, what means that the torque is cut off only after triggering the brake. By clicking on the OK button, the configuration is saved and the menu closes. Now that we have enabled the input Stop2Reset, we can connect the signal of the reset. Next, we route the outputs enable torque, enable brake, amplifier off, stop request and slope active to the CPU logic. Therefore I switch in the left sidebar to outputs. Take the bits 3 till 7, place them behind the function block SafeStop and connect each bit to one of the 5 outputs. After that, we switch to the CPU logic. Now it's possible to integrate these signals into our configuration. For example, we can connect the bit enable torque via a routing end-to-end function block to the drive save torque off, which switches off the torque of the drive system. The further configuration of the CPU logic depends on the application, so I'm going to finish the configuration at this point. Last but not least, I want to do 2 short examples to give you a better understanding what happens with the signal values of the in and outputs of the block SafeStop, when on the one hand a SafeStop1 and on the other hand a SafeStop2 is triggered. At first, we start with the activation of the SafeStop1. Let's assume that the system works correctly, what means that there is no error and the drive operates in a permissible speed range. In this case, input SafeStop1A is high because it gets a high signal from the eStop. The input SafeStop2A is also high because it gets a high signal from the output monitor status of the function block speed monitor. Apart from that, also the outputs enable torque, enable brake, amplifier off and stop request are high. If now the eStop is triggered, the input SafeStop1A goes low as soon as it gets a signal from the e-stop. At the same time, also the output stop request goes low, while the output slope active goes high, because the stop ramp is activated. Now the drive is decelerated via an emergency stop ramp. When the current speed is below the standstill limit, then the output standstill of the function block speed monitor goes high and is routed because of the jump address to the input standstill of the block safe stop. The result is that the outputs enable torque, enable brake and amplifier off go low. At the same time, also the output slope active goes low again, because the stop ramp is no longer active. To reset the safe stop 1 and thus the system, the signal of the e-stop has to go high again. Now let's have a look at the safe stop 2. At first we also assume that the system works correctly and the drive operates in a permissible speed range. Therefore the inputs safe stop 1A and safe stop 2A are high again, as well as the outputs enable torque, enable brake, amplifier off and stop request. If now the current speed on the input motion of the function block speed monitor exceeds the speed limit, which is selected by the input speed enable ID, then the output monitor status goes low. This low signal is then routed to the input safe stop 2A of the function block safe stop. Because of the low signal at input safe stop 2A, the output stop request goes low and the output slope active goes high, because the stop ramp is active. When the current speed limit is below the standstill limit, then the output standstill of the function block speed monitoring goes high and is routed because of the jump address to the input standstill of the function block safe stop. Now in contrast to the safe stop 1, the outputs enable torque, enable brake and amplifier off remain high, while the output slope active goes low again, because the stop ramp is no longer active. To reset the safe stop 2, a rising edge from the reset in the CPU logic has to be passed to the input stop 2 reset. So that's it for the tutorial about the function block safe stop. If you need further information about the safe stop, then you can take a look at the online help or the operating instructions on sic.com/drivemonitor. Now, after you got to know the function block safe stop, you are able to create a typical MOC logic. In the next and last tutorial of the chapter, Function Blocks within the MOC logic, we are going to take a look at the converter function block speed to laser scanner, which is particularly important in HEV applications.